Hi everyone. This time we're going to dig a little deeper into electromagnetic waves. We're going to look at energy considerations, how electromagnetic waves carry energy and momentum. So let's get started. Here is a little reminder of some energy related information. Power is how much energy is transmitted per second. So it's how much energy per unit time there is, and it has units of watts, right? It's the rate at which energy is produced or used or transmitted. Intensity is how much energy is transmitted or arrives per second per unit area, right? So if I look at how much light is on a certain area, the more light I get per square meter, the more energy I get per square meter, the higher the intensity. So here's a sort of a simple example here. The strongest laser in the world, well, this was a couple years ago, is 1 petawatt. So a petawatt is 10 to the 15 watts. Okay, but they can only fire in pulses of 1 picosecond, and pico is 10 to the minus 12 seconds, right? So let's see how much energy is in a pulse, and what is the intensity if the radius of the laser is 1 millimeter. So let's see, what is the energy in 1 pulse? So from the equation for power, we have that the amount of energy would be equal to the power times the amount of time. So the power is 1.00 times 10 to the minus, to the plus, 15 watts. And the time is 1.00 times 10 to the minus 12 seconds. So the energy in 1 picosecond pulse will be about 1,000 joules. All right. What is the intensity? If the laser had a radius, here's the laser, if it had a radius of 1 millimeter, right? Millimeter. So if that were the radius, then we get the intensity is the power divided by the area, or the power which we have divided by the area, which is pi r squared. And when we plug in all those values, we get about 3.18 times 10 to the 20 watts per square meter. That's a lot of energy, but it's a very short pulse. Next example, consider a TV station that broadcasts isotropically at 1 megawatt. So isotropically means it broadcasts the same energy in all directions, which is not how they generally do it, but for our purposes, it's good enough. So here's our TV station, and it is broadcasting 1 megawatt. So that means, every second it's putting out electromagnetic waves worth 1 million joules. So what is the intensity of the signal when it reaches Proxima Centauri, which is 4.23 light years away, roughly? So that is pretty far away, right? So 4.23 light years is 1 light year is the distance that light travels in 1 year. That's a very large number. And when you calculate it, it's approximately, if you were to convert it from light years to meters, it's approximately 4.0 times 10 to the 16 meters. So very far away. And that's how far. So what is the intensity? The further away it is, the lower the intensity is going to be. So our knowns are, of course, that the power is 1.00 times 10 to the 6 watts. The distance is 4.0, 0 times 10 to the 16 meters. So to calculate the intensity, it's just power divided by the area, right? Which is power divided by pi r squared. And when we plug in our power and our r, it is a very low intensity, about roughly 4.97 times 10 to the minus 29 watts per square meter. So the intensity goes down quite a bit. Don't know if they'll be able to pick up the TV shows. Okay, so one thing to keep in mind is the sun puts out a certain amount of light, and by the time it reaches, as it gets closer and as it gets further and further away from the sun, the intensity of the light goes down. And when it reaches the outside of the Earth, the atmosphere, it's about 1367 watts per square meter. So that's the intensity of the sun when it's at the surface, right before it goes to the atmosphere. But when it reaches the surface, it's more like 1,000 watts per square meter, right? A lot of the light is absorbed and re-emitted by the atmosphere. So not all the light makes it through the atmosphere. So these are just numbers to keep in mind when we're looking at the intensity of the sun. These are approximate numbers. And the distance from the Earth to the Sun changes a little bit, right? So these numbers go up and down around the year, and depending on the behavior of the Sun. And also, it also depends on how it's hitting the surface of the Earth. Remember, the intensity will go down as, when the Sun is lower in the sky, all those beams are spread out over a wider area. So, if it's straight up, if you're like directly underneath the Sun, which happens in certain parts, between the two tropics, between the Tropic of Cancer and Tropic of Capricorn, certain times a year, the Sun can be directly above you. All 5 rays from this Sun would hit that area, but that same area at an angle, only, let's say, 3 out of those 5 rays would hit it. So the energy would be spread out. And something we've seen in the past is the energy density. It turns out the energy stored in an electric field, you can show that the energy density of energy stored in an electric field is 1/2, for a uniform electric field, is 1/2 epsilon naught E squared. In other words, that's how much this here has units of joules per cubic meter. So this is how much energy is stored per cubic meter of an electric field if the electric field's uniform. So this was shown in 240, and you can show something similar for magnetic fields. There's a certain amount of energy stored in the magnetic field, right? So we have energy stored in the electric field per cubic meter, energy stored in the magnetic field and the electric field per cubic meter. Now, if we do this specifically for our electromagnetic waves, where the amplitude of E is related to the amplitude of B, and the speed of light is still this, you can show that the energy density of an electromagnetic wave is equal between the electric and the magnetic fields. In other words, what this is saying is that the energy stored in an electromagnetic wave, as it's carrying energy along with it, is split evenly between the electric field and the magnetic field. That's kind of cool. The total instantaneous energy density in an EM wave is the sum of those two. So you can write it in terms of, by using all these relationships, you can write in terms of either electric fields or magnetic fields. The average density, if you average it out over a wave, this is the instantaneous, given an instantaneous value of E, but on average, it's about 1/2 epsilon naught E naught squared, or that. So that's the energy density stored in a wave. Okay, and it's evenly shared between electric and magnetic fields, which is kind of cool. Now, brace yourselves. This is very exciting. Brace yourselves for the most ridiculously, hilariously named thing in physics. The Poynting vector. That's right, Poynting vector. Named after Sir John Henry Poynting. Old guy from a long time ago. He derived, it's beyond the scope of this course to derive it, but he derived an expression for a vector that points in the direction of propagation that the wave is traveling. And it's 1/mu0 E cross B. So if you have an expression for the electric field, an expression for the magnetic field, and you take their cross product, you get a vector that points in the direction that it's traveling. It has units of watts per square meter, which means that it is energy per second per unit area, i.e. its intensity, and it's also the rate of energy transfer per square meter. So it is how much energy is transferred per square meter by the wave. And you can do a derivation where you average this out over a wavelength, and you can get the average value for an electromagnetic wave. It's either 1/2 epsilon naught C magnitude of E squared. If I replace the magnitude of E with the magnitude of B, I can rewrite it like this, or I can have one of each. All 3 of these give you the same result, but it is the average intensity carried by an electromagnetic wave. So we can use this to help us understand energy being carried by an electromagnetic wave. So let's look at an example here. So let's say a plane wave has an intensity of, the magnetic field has an amplitude of 0.15 millitesla. Let's find the amplitude of the electric field and the intensity of the wave. Well, so we're given that the amplitude of the magnetic field is 0.15 millitesla, which works out to about 1.50 times 10 to the minus 4 Tesla. So to find the amplitude of the electric field, we use this sucker over here, right? So E naught is equal to B naught times C. And if we plug in our values, we get an amplitude of about 4.50 times 10 to the 4 volts per meter. And for the intensity, well, we have 3 equations to choose from to calculate the intensity, because the intensity, remember, is just the average Poynting vector. So I'll use the the one that is C over 2 mu naught times B naught squared. C is 3 times 10 to the 8. Mu naught is 4 pi times 10 to the minus 7. B naught is given as 1.5 times 10 to the minus 4. So we can get our value there, and I get approximately 2.7 times 10 to the 6 watts per square meter. What's next? So the intensity of direct sunlight at the top of this atmosphere is about 13.67 watts per square meter. What are the amplitudes of the electric and magnetic fields? So this is assuming that the sunlight is just one electromagnetic wave. Of course, it is a lot of different waves of all different wavelengths and things like that, but let's just assume it's one electromagnetic wave. What is the electric and magnetic field? Well, we can use this, right? We can use, well, the fact we're given the intensity, which is equal to S average, is 13.67 watts per square meter. We're going to use the equation that S average is equal to 1/2 epsilon naught C E naught squared, and we're going to solve for E naught. Solve for E naught. So if we move things around here, let's see. If I solve this for E naught, I get 2 times S average over epsilon naught C square rooted. I believe I inverted that correctly. If we plug in all our values into there, right, we plug in our intensity. Here, I'll just write some of these down just for old time's sake. So 2 times 13.67 watts per square meter divided by permittivity of free space, which is 8.85 approximately times 10 to the minus 12, and that has units of newtons. Oh no, I believe it's meter squared per newtons coulomb squared. I believe I got that right. If I got that wrong, it's not the end of the world. You can look it up. And the speed of light times 10 to the 8 meters per second. And when I get all that, I get approximately 1005, and I'm going to assume the units work out. It's a long way to get those units. So that's the amplitude of the electric field. And to get the amplitude of the magnetic field, all you need to do there is just do that B naught is equal to E naught over C. And we get approximately 3.38 times 10 to the minus 6 Tesla. Or, if you want to be fancy about it, 3.38, and I do want to be fancy about it, micro Tesla. Okay? So, what else we got? Now, we're going to look at this application to something really cool. Radiation pressure. Why is it taking so long? There we go. Radiation pressure. So, we can do a derivation, or a derivation can be done beyond the scope of this course, but basically it turns out that light carries momentum. Because it carries energy, it turns out it carries momentum, but light doesn't have any mass, so it's a different kind of momentum. We're going to learn more about that later on, but you can show that the pressure, the radiation pressure created by light is equal to the intensity over C if the light is absorbed. In other words, light being absorbed by a material is going to exert a force on it, right? And this concept has been extended to the idea of creating solar sails, which have been tested and been shown to work. That if I open a sail that is if I open a sail and I reflect sunlight off of it, it'll get twice as much pressure, by the way, than if I absorb it. So here is the pressure if I have a solar sail that reflects all the light, and here's the pressure if I have a solar sail that absorbs all the light. But it turns out light hitting something will exert a force on it. It doesn't have mass, but it does carry some form of momentum, and it can exert a force on things. And we can do some cool examples of that. So let's say, for example, we have sunlight falling on a black square. So I have a black square that has a length of 1 meter and a mass of 1.2 kilograms that absorbs all the light. So we can find the pressure on the square and the force on the square. So just for fun, let's do that. So if I were to calculate well, we're given all the information here. Let's just sort of rewrite down everything we know. We're given that the intensity of the sunlight, also known as S average, right, which is also the intensity, is given as about 1050 watts per square meter. We're given the length, it's 1 meter. We're given the mass of this thing, it's 1.20 kilograms. And we're asked to find pressure. So we're told that it absorbs all the light, so the pressure due to the radiation will be S average over C. So basically just our 1050 watts per square meter divided by 3 times 10 to the 8 meters per second. So that's going to be a very small number, right? We end up with 3.5 times 10 to the minus 6. So pressure is force per unit area, right? So it's newtons per meter squared, which is also Pascal. That's a very small pressure. How much force is that? Well, remember, pressure in general is force divided by area. So that means I can get the force. It's going to be equal to the pressure, in this case the radiation pressure, times the area. So the pressure we just calculated, the area is going to be L squared, right? Radiation pressure times L squared, because it's a square of side L. And so that gives us force of 3.5 times 10 to the minus 6 newtons. That is a very, very small force, right? It's almost nothing. Quick note, so this is like a bonus here. What would be the acceleration? Well, acceleration would be force divided by mass, right? So it would be the force we just calculated divided by the mass, which is 1.2 kilograms. So the acceleration would be 2.9 times 10 to the minus 6 meters per second squared, right? It's not going to accelerate very quickly. What would the force change if the square was perfectly reflecting? Well, if it was perfectly reflecting instead of absorbing, then it would be twice the pressure, which means twice the force. So the force would be twice that, right? So the force in this case would just be twice what we got before, so about 7.0 times 10 to the minus 6 newtons. So it would be about twice as much. How about this? What if I took a really powerful laser, a 10 megawatt laser? This is a lot stronger than like your handheld lasers, right? And I were to fire it at a dime. I looked up values for a dime. So this is a 10 megawatt laser and I'm firing at a dime. And so radiation pressure tells us that this dime should start to accelerate. Let's figure it out. So we have all kinds of information. Let's write down all the information we have. Always a good idea. So we have the power is 10 megawatts. So that's 10 times 10 to the 6 watts. We have the diameter of the beam, 2.50 times 10 to the minus 3 meters. We have the mass of the dime, which is 2.268 grams. So that would be that times 10 to the minus 3 kilograms. We have the diameter of the dime, which is 17.91 times 10 to the minus 3 meters. So let's do it in steps. Let's just start with what we want. We want the acceleration, right? So the acceleration, good old F equals ma, right? So the acceleration is going to be equal to the force divided by the mass. So force, well, to get the force, remember that the pressure is equal to force per unit area. So that means force is equal to pressure times area. In this case, it's radiation pressure. So now we have acceleration is equal to the radiation pressure times the area divided by the mass. So now I'm going to assume that the light is 100% reflected, right? If the light were 100% reflected, sun would get absorbed, and I imagine that dime would heat up and start melting very quickly. So let's assume it's a perfectly reflecting dime. Why not? And we're going to say, all right, we're going to say it's perfectly reflecting, so I can use this for my pressure. So now I have my pressure is 2 times S average times the area over the mass times the speed of light. Now I'm going to use that S average is equal to the intensity, right? And the intensity is equal to the power per unit area. So I'm going to plug in S average is equal to power per unit area. So what do we have here? We have 2 times power per unit area times the area divided by MC. This is going to be nice. So let's see, areas cancel. We end up with 2 times the power over MC. So if I were to do this calculation real quick, let's see. It's 2 times the power, and our power is 10 times 10 to the 6. And it's divided by the mass of our dime, which is, I believe the mass of our dime, 2.268 times 10 to the minus 3. And divided by the speed of light, right? 3 times 10 to the 8. And what do we get when I do that? I get approximately, good. I get approximately 29.4 meters per second squared, which is, approximately 3 times the acceleration due to gravity. So the dime will start to accelerate, assuming that the dime doesn't melt because it's reflecting everything. But that's kind of a cool, calculation. What's next? Oh, here. How long would it take if I took a common laser pointer? I'm going to be generous and say it's a 5-watt one, like one of those handheld ones, and I fired it at a perfectly reflecting Honda Civic, a green Honda Civic. The green doesn't matter. How long would it take that Honda Civic to reach 10% the speed of light? So calculate the acceleration of the Honda Civic due to this radiation pressure. And this is one that I would like you to do. It's fun. How long would it take? Let me do one last example here before we go into something else. Solar radiation, just before reaching the Earth, has intensity. I'm going to approximate it here as 1.4 kilowatts, right? 1,400 watts per square meter. If we treat the Earth as a flat disk perpendicular to the radiation, what is the radiation pressure? What is the force due to the radiation pressure? In other words, what's the force due to sunlight pushing the Earth outwards? And then see how does that compare to gravity? And you might correctly assume that the force outwards due to the radiation pressure is not going to be as strong as gravity, nearly as strong. So let's try it out. So keep in mind it's like this, right? Here's the Earth disk, right? And we have sunlight coming out like this. And we're assuming that we have let's assume it's a reflecting Earth again. So let's calculate it. The radiation pressure would be 2 times S average over C. And you plug in our S average. So remember, we got that S average. We're given that the intensity is 1.4 watts per square meter. So what is the intensity? The pressure? I get about 9.33 times 10 to the minus 6 Pascal. Now, if I wanted to calculate the force due to that, right? So the force due to the radiation pressure, would be the radiation. Remember, pressure is force per unit area. So it would be the radiation pressure times the area of that circle of the Earth. So we need the radius of the Earth, by the way. And that works out to, I had the radius of the Earth here, 1 sec. Radius of Earth. It's about, I don't want it in miles. In meters, it's about 6.371 times 10 to the 6 meters. It's a big Earth. Well, it's the only Earth. So this would be P rad times pi times the radius of the Earth squared, right? And when I do that, I get roughly 1.19 times 10 to the 9 newtons. So assuming the Earth is reflecting all this, that seems like a pretty big force. And it is. I mean, it's nothing to sneeze at. But if you compare it to gravity, right? The force due to gravity is going to be G times the mass of the sun times the mass of the Earth big numbers, all over the orbital radius of the Earth squared. If I were to plug in everything there, I get about 3.52 times 10 to the 22 newtons. So look at the comparison of those two, right? The force of the sun is so much more than the force due to the radiation pressure that you can safely always ignore the radiation pressure. How about this one here? What if I have a 500 kilogram satellite and I launch it and it opens a solar sail that is 1 kilometer square? What is its acceleration due to solar pressure? And how far will it get in 1 year? Right? So here's my little satellite, and it opens a sail that has an area of 1 kilometer squared. And that's about 1.00 times 10 to the 6 meters squared. Right? And it has a mass of 500 kilograms. Right? And the intensity of the light just outside the Earth is roughly 1400 watts per square meter. So, we can do everything here. We're going to use our equations, right? We're going to use that P radiation is 2S average, or 2 times the intensity over C squared. This is also S average. We're going to use that pressure is equal to force per unit area, or the radiation pressure is the force due to radiation per unit area. We're going to use that acceleration is force divided by m. So to solve this, I would say, all right, let's find the acceleration. It's force per unit mass, and force is equal to the area times the radiation pressure per mass, and that is equal to 2 times S average times the area or what am I missing here? 2 times S, so taking radiation pressure 2 times average over Cm, right? And if I were to calculate all of this, I get that the acceleration is approximately 0.01867 meters per second squared. So it's a very, very small acceleration, right? That's like 100th of the acceleration due to gravity. So if it was just, this is for, what is the acceleration here? Now, if I wanted to find how far will it get into the year due to this acceleration, well, delta t of 1 year, that's approximately, it's 5,200 minutes. There's a song about that. And also in seconds, 3.154 times 10 to the 7 seconds. So if I want to know how far will it get in 1 year, I would say, well, the distance traveled is 1/2 acceleration times time squared. Okay. And when you plug the numbers in for that, you get 9.29 times 10 to the 12 meters. So that's pretty far. How far is that in terms of astronomical units? Well, 1 AU in meters is 1.5 times 10 to the 12. So 1 AU is the average distance between the Earth and the Sun. So this is like 40 times that. So, if you had the acceleration due to just this solar sail over a year, it would get to 40 times further away from the Sun than the Earth, roughly. But there's something wrong with this, right? We assume that we didn't even include gravity. So there would be a force of gravity on this sail at this point. So there are other concerns, of course, but this is just to give you an example of solar sails.